Alrighty, thank you, Sheena. Again, my name is Nicole Bonnett, and I will be your moderator for today's panel. I'm a first-year PhD student in the School of Urban and Regional Planning here at the University of Alberta, and I am a senior research assistant in the Climate Adaptation and Resilience Lab. So just again, first of all, thank you to everyone for taking the time to attend this panel. Conferences and panel discussions are a little bit different this year, and we really do appreciate the continued support and engagement. So let's get this thing going. As Sheena briefly outlined, today we have an exciting panel on sun, fire, and water, optimizing climate change response with artificial intelligence. This panel is going to shed light on how artificial intelligence, or AI, can be harnessed to effectively slow down climate change through mitigation and adaptation, as well as to better manage renewable resources. We have three panelists who will reflect on the use of AI in the context of sustainability by examining three separate research projects. So the first is on harnessing solar energy to reduce the use of traditional non-renewable energy sources. Second up, we have fighting fires to mitigate deforestation. And last but not least, improving the effectiveness of water treatment to increase our water reuse. So let's introduce our panelists. First up, we have Moosa Moghimi with a PhD in energy systems from the University of Alberta in 2017. Moosa has now joined the computing science department, and his research interests include power distribution systems and application of artificial intelligence in power systems. Next up is Jessica Zerb. She is a master's student in the Department of Renewable Resources, and her research focuses on applying machine learning techniques to forecast fire weather indices. And last but definitely not least on our panel is James Bell. James has an MSc in neuroscience and computing science here at the U of A and is currently a research associate in the Department of Computing Science. His research focuses on applying reinforcement learning to real-world problems. So each of our panelists are going to have a 10 to 15 minute presentation. At the end of each presentation, we're going to allow for a brief 3 to 5 minute section for quick audience questions. So if you've got a burning question that you'd really like to ask, just feel free to unmute yourselves. You can comment in the chat or raise your hand. Further, at the end of our panel presentations, there's going to be a 30-minute slot for Q&A. So we're looking forward to an exciting and informative discussion. And with that, we'll get started. So the first to present on the sun aspect of our panel is Moosa. So you can go ahead and take it away, Moosa.
Okay. Good afternoon, everyone. My name is Moosa Moghimi. I'm a postdoctoral fellow at the Sustainable Computing Research Group here at the University of Alberta. And today I'm going to talk about our research on energy storage system control for voltage regulation in power distribution systems with high photovoltaic penetration. First, I'm going to give an overview of electrical power systems, the major components, and then I'm going to talk about renewable energy resources, specifically solar generation, and the advantages they offer, and also the problems that they could bring to the system. More specifically, I'm going to talk about the voltage problems in distribution systems, and then I'm going to talk about how reinforcement learning can help us solve this problem, and why we think reinforcement learning is the proper solution to address this problem. And finally, I'm going to talk about our future work and the next steps we're going to take on this research. So here's an overview of the power systems. We have like 4 major parts. The first one is generating a station. This is where the electrical power is generated. Like these power plants transfer like electricity from fossil fuels typically, or other sources, hydro, renewables, to electrical power. Then we need to transfer this power to the consumers, because typically these power plants are far away from major cities and consumers. So we need to have these transmission lines to get the power from generating a station to substation, where we step down the voltage and distribute this power to the consumers, which could be industrial or residential. This pie chart shows the major sources that we use to generate the electrical power here in Canada. As you can see, around 2/3 of this electrical power is being generated from fossil fuels, which means carbon emission, which means air pollution, and obviously these are the things that we need to change. And right now, only 3% of this power is being generated from renewable sources. The next thing I need to mention is that these power plants are not that efficient. Like the typical efficiency is between 30 to 40%. So we are wasting a lot of energy to generate this electrical power. Then we need to transfer this power to the consumers via this transmission network, which again adds another 6 to 8% of losses. Obviously, we don't want to have these losses. So what's the solution? We can kill two birds with one stone if we could install renewable sources in distribution system. So the advantages are, first, we are using renewable sources, so no carbon emission. And second, we are generating the power right where we want to use them. So there is no need to have those transmission lines. In addition, like over the years, with increasing population, with increasing like demand, those transmission lines have to be updated, which are like costly and cause additional like impose additional difficulties to the network. But with distribution, with distributed resources in the distribution system, we can solve all of that problems. And fortunately, the PV cell prices have been reduced drastically over the past decades due to like the technology being mature now. And this chart is a little bit old, but you get the idea. Now these PV cells are really affordable, and that's like one of the major reasons that PV has gained a lot of interest in recent years all over the globe, and more solar panels are being installed in the electrical systems. Now, is there any problem with having too much PV generation? Let's take a look at the typical PV generation. So as it is expected, the maximum power generation from solar panels happens around noon. But the problem is the maximum load demand happens at early hours, early evening hours. So what does this mean? So let's take a look at the typical distribution system. Let's put 4 PV panels and let them just generate the maximum power that they can generate without any control. So if we like run this simulation and take a look at the voltage levels at one of the nodes in the network, we can see that at around noon, we have these over voltages in the network. These over voltages are not safe for the equipment, for the consumers. That's one problem. The second one is that this extra PV generation could lead to inverse power flow from the consumer side to the utility grid. And this is like a major issue for the protection system, because traditionally these protection systems are designed to deal with the power flow, unidirectional power flow from the grid to consumers. So how could we deal with this problem? What are our options? Of course, we have traditional voltage control tools to deal with voltage issues, but there are some problems here. First, these tools like step transformers or capacitors are not designed to deal with the fast changes in the renewable sources. Like solar power generation can quickly change due to a cloud or some other reason, and the voltage can change quickly, and these traditional tools are not just designed to deal with this, and overusing them could drastically reduce their life cycle. And in addition, these tools are typically designed to deal with under voltage problem, not over voltage problem. So what is the next option? The next option is to just cut down the PV power generation. It means that when we have like too much PV generation, we're starting to see like over voltage issues over the network. We force the PV inverter to reduce the PV generation to alleviate the problem. Obviously, this is not an optimal solution because we invest a lot in our PV panels, then we are forcing them to work at a lower efficiency. The next option is reactive power compensation. Means that to deal with the extra active power that is being injected to the grid, we draw some reactive power to keep the voltage within the safe limits. Again, this is not an optimal solution because we are not using the PV inverter capacity at its maximum. So what is the remaining option? It's energy storage. And the idea is pretty simple. We store the energy when we have extra power available, so we can use it later on in the day when we have a like peak in load demand and we don't have a like PV generation anymore. So it's kind of like we are shifting the load, shifting this power generation. We store it around noon and we use it at the evening. So let's take a look at our system. And this time we consider 4 energy storage units or batteries at each PV's location. Here we need to solve a convex optimization problem after some linearization. But again, we want to like minimize the utilization of these batteries to have the maximum lifespan, but subject to we need to like keep the charge or discharge power of the batteries within the like allowed limits, lower than the maximum rates. And of course, the state of charge or SOC of the batteries should remain between the like minimum and maximum levels to make sure that the life spans are at their maximum. And finally, as we discussed, we want to keep the voltage levels between the minimum and maximum allowed levels. So this is a like convex optimization problem which can be solved with any optimization package and over the like course of the day. So if we solve this problem and we take a look again at the voltage profile, now we see that voltage is always between the minimum and maximum and we don't have any problems anymore. So we solve this problem pretty easily. We don't have any problem anymore and we didn't even need to use AI, right? Actually, no, there's one tiny detail that I didn't mention, and that's the function that relates these voltages to these injected battery powers depends on the parameters of this network. And in reality, we don't know these parameters because for distribution systems, the system operators just don't keep track of these parameters. Maybe they have some initial estimation, but over the years, these parameters could change due to aging, due to maintenances and other stuff. And also, the system operators frequently change the configuration of this network. So we don't know the parameters and even the configuration of this network. So obviously, we cannot solve this optimization problem if we don't know the parameters. So what's the solution? Here's where reinforcement learning comes in. We can have a model-free approach that can adapt to the changes in the system using RL. The way we approach this is to place an RL agent at each solar panel's location, at each energy storage unit location, and this agent is responsible to adjust the charge power of or discharge power of these batteries. So the agents take some action, which is in terms of charge or discharge power, and they receive some reward from the environment, from our distribution network. Then they can readjust their action to eventually reach the optimal action. I should mention that this is an ongoing research and we are still working on this. Specifically, we are working on designing the proper reward signal. But this is the next step in our previous work, which was controlling the charge power of electric vehicles in the distribution system to avoid voltage problems. So now we are adding the solar generation, and now we have batteries. So batteries, unlike electric vehicles that can only be charged at a lower or higher rates, batteries can both charge and discharge, which makes the problem more complicated. So right now we are working on our multi-agent reinforcement learning platform, and we are working on designing the reward signal and the training phases, and we want to consider the fairness or SOC balancing between the batteries, because we want to utilize all the batteries at the same level, so that the lifespans, like the lifespan of one of the batteries is not much shorter than the others. And of course, we want to study the adaptability, study if our agents can adapt to the change in the network. And after we are done with this stage, we also want to consider the time of day pricing. So it's like introducing an additional objective to the work. So because some utilities have different prices for electricity over the course of the day, the price could change. So we want to somehow optimize the revenue we can get from these batteries. So the idea is pretty simple. We store the energy at the hours that electricity is cheaper, so that we can sell it back when the prices go up. And finally, we want to add electric vehicles to have a full picture with renewable sources, with energy storage units, and with electric vehicles. And we want to see if our multi-agent RL framework can handle all of these at the same time. If you have any questions, I'd be happy to answer them right now. Or if there's anything that you want to follow up with me, please feel free to contact me at my email. And thank you.
All right, thank you, Moosa. So it is 2:51. We've got a good 4 to 5 minutes for any questions if you guys have. Again, just feel free to unmute yourselves or comment in the chat, raise your hand, whatever works. Okay. We have a question here from Melanie. How do electric vehicles change the problem of power distribution?
They just add additional uncertainty, because first, they largely increase the scale of the problem, because with PV panels, especially the larger ones, we only have a few in the system. But in the same system, we could have hundreds of electric vehicles. So the scale of the problem goes up rapidly. And then we have additional loads. And these electric vehicles can draw a lot of power. So we have an even higher peak in the afternoon, right? So now we need to also consider this additional uncertainty and this higher scale of the problem.
Awesome. We've also got another question here from Anne asking about affordability. You could comment on that.
It depends. We haven't done any economical study on this yet, but the thing is, energy storage units are becoming more affordable. I guess I should have included some slides on the price of energy storage as well. But big companies like Tesla are picking up on this, and now we have more affordable units than before. And specifically, if we consider over the long term, and I'm talking from the utility point of view, or the long term, if we could avoid installing, let's say, a new transmission lines, which is inevitable, right? At some point, the demand goes up and the current transmission system cannot handle that. So we have to install some transmission lines, which cost billions of dollars. So at that point, avoiding that cost by buying some energy storage units would make total sense.
I think we have time for one more question. So Rahim is asking, what are the results of the research reducing variability using RL agents in the network? And has this been tested in an operational system or just simulations?
No, with this PV panels, we are still at the simulation phase. But the thing is, I don't think we can right now put it to test at a operation, in practical case. But with that EV charger, there was some test platform that we were able to somehow like simulate the performance of our multi-agent RL platform. And the results are published in the paper or that I referenced in the slides. I can like share them with everyone if anyone is interested. So, but I'm not gonna go through details of that because obviously it didn't have PV.
All righty, well, thank you to everyone for those very engaging questions. And thank you, Moosa. Your description of reinforcement learning and your justification of energy storage was very insightful. At this time, we are going to move on to Jessica, and she is going to comment on the fire aspect of our panel. So whenever you're ready, Jessica.
Okay, so hi everyone. Thank you for attending this session. Before I dive into my presentation, I want to take this opportunity to thank my supervisors, Mike Flanagan and Piyush Jain, for their dedication to fire research and the guidance they've provided me throughout my thesis. Thank you to the Sustainability Week Council for organizing this event and bringing light to the importance of sustainability. So like Nicole said, my name is Jessica, and this is towards seasonal forecasting of fire weather using neural networks. Okay, so to provide some structure for this presentation, here's a rough outline. We'll begin with the purpose of this project, an introduction to various terms and ideas, some methods used, some results that I obtained early on in the project, and where I am currently at with my research. Okay, so as many of us know, out of control wildfires can lead to devastation among communities and can cause lasting ecological damage to established forests. In particular, in Alberta, the 2011 Slave Lake fire, which is shown in these images on the left here, destroyed 374 homes, left many damaged, and also left 732 residents homeless. The 2019 to 2020 Checkhead Creek fire, which was unofficially known as the High Level Fire, forced 5,000 evacuees and burned an estimated of 300,000 hectares and lasted 17 months. So it actually started on May 12th of 2019 and only ended this year on October 13th. And our neighbors in BC experienced one of the worst fire seasons on record in 2018. This is an image from the 2018 Syringa Fire Complex, which is actually where I found myself entering the world of firefighting and fire research. The heavy smoke from many fires throughout the world, throughout the province blanketed cities across Canada. And while I was working in Calgary at the time, and I spent almost every weekend in the mountains hiking or climbing. So the smoke and its negative effects on everyone's health and well-being was undeniable, also to myself. So my concern and interest led me to pursue wildfire fighting in BC. And after that season, I returned to Edmonton and worked as a spatial data analyst for the Canadian Forest Service. A year later, I started my master's in fire research and more specifically, seasonal forecasting. And this can be used as an early warning system to communities at risk. And hopefully the fruit of this research can allow for fire management to deploy fire mitigation strategies in advance. For Canada specifically, Indigenous groups are highly impacted by wildfires and as a result, climate change. Climate change effects have led to drastic warming in the north, and as a result, the effects of climate change are thought to be larger in the north by comparison. So eventually these problems will worsen, and it's imperative for us to deploy some form of early warning system to help these communities. And here are just a few images of my time as a wildfire fighter, although the image on the right is from some fire research in Alberta that we did. Wildfire fighting, more generally fire and forest management, is aimed at protecting communities and forests. Our forests are a crucial sustainable resource that can be preserved with the use of AI. And right now there is a lot of development with respect to the fire research, but there's not a lot of use in it operationally, but eventually these will come as research progresses. Okay, so we know, so how do wildfires occur? So we know that fire requires oxygen, heat, and fuel to ignite, but sustaining wildfires requires more than just that. And so this is the wildfire behavior triangle, and we require the correct weather, topography, and fuel to ignite a wildfire and for it to propagate. So my thesis focuses mainly on the weather aspect of this behavior triangle. Okay, so what is fire weather? Fire weather can be better understood by the fire weather index system. And so this table consists of 6 components that account for the effects of fuel moisture and weather conditions on fire behavior. So we can actually see the first 3 components outlined by fuel moisture codes. These are numeric ratings of the moisture content of the forest floor and other dead matter. Their values rise as the moisture content decreases. And the remaining 3 components under the fire behavior indices category represent, so ISI, or initial spread index, represents the rate of fire spread. Buildup index, or BUI, is the fuel available for combustion, and FWI, or fire weather index, is the frontal fire intensity. And these values all 3 of these values will rise as the fire danger increases. And so for my preliminary results, I'm just going to focus on forecasting the buildup index, or the BUI. And so now we move to understanding the methods that I use for forecasting FWI indices. And I use a neural network. So a neural network maybe isn't as complicated as one may think. It turns out you don't have to be in the matrix to know what's going on. So this is just a simple neural network with one hidden layer. And essentially, a neural network is a learning system that uses a network of functions to understand and translate a data input of one form and produce a data output of another form. And so the network of functions lies within this hidden layer in the middle, which is shown by these red circles. And you can essentially think of this layer as a regression function. So it's basically just trying to figure out the relationship between 2 variables. And the concept of a neural network was motivated by how a human brain functions and how neurons fire. But before we can apply any sort of neural network, a great deal of time was spent pre-processing our data. So we actually collected all of our FWI indices from all of the Environment Canada weather stations from 1959 all the way to 2014. And we used Voronoi tessellation to interpolate the FWI values into each ecozone. So these are the ecozones here. We took a weighted mean of the FWI indices, and this resulted in 1 value per month of each index. And so we used in the previous, in the next slides, I referred just to the Mixedwood Plains ecozone for initial testing. And I should also mention that for the initial testing phase, we started by using a univariate long-term, short-term memory model or neural network to forecast just BUI indices from past BUI indices. And we used the 70-30 rule for training, validation, and testing, and we're exploring other data deviations like 80-20 and whatnot. Okay, so here are some of the results, or I guess just the very initial results. We can see that the red line represents the model predictions. The green line is the climatology, which is just a monthly mean of all the data. And the blue line represents the FWI indices, and the blue line represents the observed FWI indices. So I showed just from 1999 to 2005 for clarity's sake, otherwise the image would be pretty busy. But we can see that the model actually outperforms the climatology, which is what's most commonly used for forecasting. Okay, and so we are eventually hoping to further improve the quality of our prediction by moving to a multivariate model. And this is where we input various data sets like different atmospheric oscillations. So for example, this here is like the Nino 3.4 index, which is a numeric rating of sea surface temperature anomalies. And this actually might be better known as El Nino or La Nina. So El Nino is the warm phase and La Nina is the cold phase. And the effects of El Nino and La Nina on Canada are experienced between 3 to 6 months after the anomalies occur. And so this is called a lag time. And by incorporating this lag time into our model and obviously the ENSO indexes, we can hopefully predict FWI values farther into the future and with improved accuracy as well. So of course, we're also trying to use other atmospheric oscillations like AMO, which is the Atlantic multi-decadal oscillation, and PDO, which is Pacific decadal oscillation. We'll also try to use climatology as a covariate. And so yeah, here are my references, and that is pretty much it.
Alrighty, thank you, Jessica. Super interesting. You've really got to be embedded right in your research topic, fighting all the forest fires, so you get to observe it directly. Again, we have a good 4 minutes for questions from the audience. Okay, we have a question from Zachary. What is Voronoi? What is this?
Tessellation. So it's just an interpolation method. So essentially, we have many data points, like individual data points, and we're trying to be able to represent a larger area by a single data point. So Voronoi tessellation essentially is an interpolation method, so it allows us to have an area that has a certain value rather than just a single point. So yeah, that's essentially, it's just a type of interpolation method.
Great. And one question here from Alexandra. Can the network account for missing weather data? For example, more remote areas without consistent weather stations?
So that's actually why we tried to take the mean of each of the weather station data, just to kind of account for these gaps in time where there isn't any data. So these weather stations take daily data readings, and they actually take not only daily, but based on time as well. So we've taken the mean to be able to combat this. So now instead of having, 5 different readings for one day, we have only one for 1 month.
Okay, and we've got a question from Sheena. How does COVID and the fact that people were moving less impact these predictions?
So we haven't really done too much research on this yet, mostly because we need to incorporate the weather station's most recent data. Right now, I've only got the model running to 2014, but of course, before we proceed any further, we'll try and include the most current data. So I can't really say how COVID has affected the predictions, but I'm sure it might be something we see in the model. I'm not entirely sure yet. I know that there are some studies on wildfire and COVID, and yeah, those studies have just recently been published. So that might be something worth looking into.
Okay, I think we have time for one more. So Eleni says, what about planning how to fight a fire? So is there an opportunity to use AI algorithms to make it more efficient?
I'm sure there is. So FWI indices aren't necessarily directly correlated to fire operations and fire management out in the field, so with fighting fires, but I'm sure that there's probably a way of using image recognition or neural networks even just to figure out the progression of a fire perimeter. So this using fire perimeter estimates maybe by using AI this can lead to more effective firefighting, because, you know, fire management will be able to target areas that they might have predicted that will expand, and, you know, the head of the fire could change drastically according to this AI prediction. So that could be useful in managing wildfire fighting.
Alrighty, thank you, Jessica. So it is 3:10. We're going to move on to our last panelist. So with some key messages on the water aspect of our panel is James. Whenever you're ready, James.
The main way that people will experience climate change and its negative impacts come through water-related impacts. I'm going to talk about one specific aspect of water impacts, dealing with water treatment, and an approach to help with that using reinforcement learning. The impact of water can be felt through flooding, through drought, and through the loss of access to clean water. Approaches to flooding and drought can potentially use AI. They can also be non-AI solutions, like the provincial government's recent announcement of funding to support flood mitigation. But I'm going to focus specifically on the loss of access to clean water. Climate change can impact this loss by the increased growth of disease and organisms in water as temperatures heat up. It can cause freshwater sources to become salty, and flooding can cause all sorts of additional contaminants to impact the water supply, so that the overall impact of climate change on water is to make a lot of our water sources dirtier. An example of this recently in the flooding in Calgary a few years ago, as water levels rose and flooded downtown, a lot of oils and other residues in the streets entered the water supply, and that makes for a much more complicated situation for the people at water treatment plants to try to deal with. So the goals of my project are to make more efficient use of raw materials, like the chemicals that are used to treat water, to help bring down the cost of water treatment. Also to reduce the energy usage of water treatment. It takes a lot of energy to run certain filtration processes, and especially in places where our electricity is mostly carbon emitting, this is a great way to reduce the amount of carbon that's produced. And the project is also aiming to allow water treatment processes to more easily adjust to changes like these dramatic weather events causing the quality of the incoming water to change. And specifically, this is the cleaning of the water supply that's coming in. This is not the treatment of dirty water like sewage. There are quite a few different approaches to cleaning water. My project is specifically focusing on ultrafiltration. This type of water treatment involves filtering water through extremely small holes, and through that process, the water can get through the holes, but pathogens, bad tastes, and other problematic compounds are blocked and can't get into the water supply. But this process is very energy intensive. It takes a lot of energy to use high pressures to force the water through the filters. Up to 44% of a municipality's energy costs can come just from its water processes, and 14% of that is specifically in these treatment stages. So energy usage can be, like any energy reductions in these stages can have dramatic impacts on the amount of energy that's used. In order to prepare the water for this filtration stage, we first have to do some pre-treatment. There are some substances in water that are so large that they'll clog up the filters and prevent them from working. So we add some iron-based or aluminum-based compounds that cause these substances to clump up, to sink to the bottom of a giant holding tank, like the one on the left side of this slide here. And then those sink down so they don't clog up our water filtration process. Also, the chemistry of these reactions is impacted by the pH of the water. So we might want to add an acid or a base to adjust the pH of the water to something that makes the overall process more efficient. And the temperature of the water can also have an impact. So maybe we want to add a heater in here, and by heating up the water, make the overall process more efficient, even though heating the water itself takes some energy. And if we do all of that process, it'll work fine for about 30 minutes. And by that point, these filters are so dirty that the pressure has to get really, really high to push the dirty water through the filters. And these filters are just going to rupture. And a ruptured filter means that all of the bacteria is getting into the fresh water supply, you get people sick, the regulatory body comes in, all the technicians get fired. So in order to prevent that outcome, after about half an hour of running, we take some of the clean water that we've used and we have to use it to rinse the filters in reverse and then discard everything that we wash off. And then we can start running the process forward again. And so then as long as we wash every 30 minutes, this water cleaning process can continue indefinitely and the community has clean water. So with that general process, we want to look at how we can optimize it. So I could start by adjusting the pH. I want to figure out what's the optimal amount of chemical to add so that the overall energy usage of the system is optimized. And then I can adjust the temperature and figure out what temperature is going to make it better. And then once I've got those in place, I could change the backwash settings. How often am I washing my filters? And then I could adjust the mixer speed that mixes the chemicals. That's going to optimize the system a little too. But once I've optimized that, I might find that all these other changes to the settings have meant that my pH is no longer optimal and I need to go back and adjust my pH. And this process can continue with a lot of iterations until I finally have the optimal settings. But this is only going to work for a single moment in time. As soon as the weather changes, I'm going to need to re-optimize my whole system again. During the winter, water is extremely clear and pure, but during the spring, as water levels rise, they're more likely to pick up extra dirt. You might have a tree falling in, and then you've got this organic material, and the water becomes a lot more complicated, dirtier, more difficult to deal with. Something similar can happen during the summer when algae starts growing, and algae adds its own complications to the water treatment process. So optimizing water treatment, we also need to figure out how to deal with these occasional seasonal effects. And then you add in more dramatic weather changes like flooding, and it's even more important that a system be able to adapt. So when we're looking for a responsive system that can think ahead, it wants to look at what's going on upstream in the entire watershed. Is there flooding happening in a community further upstream from us? Or what's the forecast for the climate or the weather in the near term? And it's very difficult to experiment on all of these things because if you do it in a real system, there's a risk of hurting people, of making people sick. So we are making use of a pilot project, a special plant that's designed just for this research. So a local company called ISL Adapt approached the RLAI lab at the U of A and got some funding from the provincial and federal governments and formed a relationship with the town of Drayton Valley to design this small scale water treatment plant that you can see here in the pictures. And so for the last couple of years, we've been designing this plant, making sure it has all of the sensors that we need in order to do this research. And just in the last month have deployed this in the facility in Drayton Valley, where we have expert technicians who are going to give us support in setting up the system, existing infrastructure, so that we can then apply some reinforcement learning to optimize the problem. So reinforcement learning is a type of AI that is really good at optimizing over time to try and make sure that a specific reward that it's seeking is optimized. So the basic paradigm is that you have some type of environment. In this case, we have our water treatment plant. And there's some type of agent. In this case, this is the algorithm, the code that's running on our computer. And we pass observations from the sensors from the environment to the agent, and it gets to decide what action it wants to take to try to control the plant. And based on what action it selects, we tell it whether it did a good job or a bad job. We give it a reward, which forms the feedback that allows the agent to know how to change its decision. So then when we give it a new set of observations, it can decide what action to take. Then we'll give it another reward and another set of observations. And it can keep acting like this and iterating over time until it gets smarter, until it gets better at making decisions. And along the way, these agents tend to make really dumb decisions as they're trying to explore and test different combinations, which is why we're running this in a small scale plant that's not providing water that humans are going to be drinking. But over time, as it gets smarter and it learns, the aim is that it will produce, of course, water that's clean and meets all the regulatory standards, but does so in a more energy efficient way. So as the plant was just built and set up about a month ago, we're just in the process now of starting to run agents on here to build this plant that will make more efficient use of materials, reduce energy use, and be more adaptive to seasonal as well as dramatic weather change events. I can take some questions now.
Thank you, James. Your presentation taught me that this water treatment process and ultrafiltration is a lot more complex and, dare I say, risky than I'd previously thought. So again, we'll open it up to questions specifically for James before we get into the open Q&A. Okay, we have a question from Joanna. Is it using data from previous years or only current data?
So we've been doing some of our research on previous years. We have about, I think, 5 or 6 years worth of data from the Drayton Valley plant. But the plant operations usually only record like maybe every 15 minutes, and that gives them some very generalized information about what's going on. And in order to make decisions as quickly as we want to, we need much more frequently updated data. So while we're learning some things from historical data, we're mostly looking forward to using the more sensor-rich and more frequently updated data from our new pilot.
I have a question. When you were talking about the impacts of climate change on water, and more specifically, when you're talking about how it makes it more salty, were you referring to, I think I remember learning about this, the impact of sea level rise and increasing saltwater intrusion into those freshwater aquifers on the coast? Or are you more so talking about coastal flooding, say, of saltwater?
It sounds like you know more about those aspects than me. So I was mainly thinking about the impact along the coast and whatever impact flooding happens there. But actually the specific type of water treatment that I'm working with doesn't deal with desalination. So dealing with that type of impact to the water supply is a whole other area.
Thank you. We've got a question from Zachary. What kind of investment would be needed to implement this algorithm into current water treatment plants? Hardware and software needed?
So from a software perspective, all that would be needed is whatever software we're developing. And I'm not sure exactly what that would look like, given the partnership between various entities. And from a hardware perspective, that's something we're exploring. We have added quite a few extra sensors to our pilot plant because we want to make sure we have as much data as possible while we're learning about what works best. But most of those sensors are within the type of cost that it wouldn't be noticeable compared to the existing budgets of these plants.
Thank you. Okay, and last question before we open it up to Q&A. Eleni says, what happens when the pollutants change?
One of the types of sensors that we are working with does a full scan of the water. It's called fluorescent spectroscopy. So it's very good at identifying different types of pollutants, and that can potentially allow these systems to adapt more to the types of pollutants, but still fundamentally, we're working with a system that's about a physical barrier that's filtering out pollutants. So if they're ones that barrier works well with, then we can adapt to that, and the algorithms will just need to learn to change over time. Maybe we have to wash more frequently, or maybe it needs longer washes, or maybe we need to add a little more bleach into the washing cycles. But the algorithms should be able to learn what happens in those cases, and hopefully also to predict as those pollutant levels are changing over time.
Awesome, thank you. So thank you to all of our panelists for such an interesting recap of how AI can be utilized to prepare for and address climate hazards and sustainability. We're going to open it up to questions from the audience, and we've got 30 minutes. But first, I did miss a question previously. So there was a question from Benjamin, and this one is directed for Moosa. So Benjamin had asked, are there any issues associated with transmitting energy from high solar potential areas, for example, southern Alberta, to low solar potential areas like northern Alberta, or has that been investigated?
Not really. Once the power is generated, power is power, right? Specifically regarding this, I know that there's a lot of wind farms in the southern Alberta, but I don't see any specific reason that why southern Alberta is better than any other part of Alberta, right? Because this is solar, there's not much difference. If there's any difference, I'm unaware of that, but I know that there are a lot of studies that show high potential for Edmonton and Calgary to install rooftop solar panels. Yeah, but in terms of transmission, power is power. There's nothing different from traditional power plants.
Great, thank you, Moosa. So we'll just open it up to Q&A at this point for any of our panelists. Nothing quite yet. I have a question, one for Jessica. Why did you choose the buildup index to be the preliminary or first metric for forecasting?
Good question. So I chose BUI initially because buildup index shows a really distinct seasonality. So essentially it's at its lowest point in the winter and its highest in the warmest month. So I chose seasonality because I was hoping that since it has such a distinct seasonality that my neural network would pick up on this a little bit easier and be able to forecast the next values easier, essentially. So yeah, that's why I chose BUI.
Awesome, thank you. We have another question for Jessica. This one's from Alexandra. She asked, how long until the AI forecasting is available for fire management agencies across Canada?
So I guess it essentially depends on how fire management agencies are looking to advance their forecasting. Well, in terms of research that's coming out right now, there isn't a whole lot, like I said, in terms of forecasting fire weather and other fire indices. So until that research is published, then hopefully these fire management agencies can actually take this into application and use it for actually fire mitigation practices. So yeah, yeah,
Called it a day.
exactly.
All right, and we have another one from Elena. For Jessica, was additional data, would you like, or what additional data would you like to have access to?
You know, I think we have a lot of options in terms of adding covariates to our model. So any sort of data that has like I was mentioning before, we're using atmospheric oscillations because they have a decent lag time. So that allows us, you know, potentially even 6 months in advance to be able to forecast values. So for example, if La Nina was happening right now, we would be able to forecast, we would hopefully be able to forecast FWI indices 6 months later. So any sort of large-scale atmospheric data would be helpful for improving our neural network. Any sort of really, large-scale atmospheric oscillation data. So I would say more oscillations. Right now, we're just focusing on 4, but if we had access to others and consistent access to that data from decently far into the past, that would be helpful as well. So, but the thing is that, you know, data recording and reporting changes, so it needs to be consistent.
Mm-hmm. That's interesting that you're looking for very broad and large scale data. In the research that I do, we're always looking for downscale data, and there appears to be a lack of that, which is unfortunate. I have a question for any of the panelists, whoever wishes to answer. What areas, countries, or demographics are suffering the most with climate change, and how can we bring these technologies to these groups? Does anyone want to take a shot?
I don't know about like climate change in general, but I know like when it comes to water, there are certainly places in the world that have more trouble cleaning water, especially when a water supply, like we are impacted here in Edmonton by things that are happening upstream in Drayton Valley, and they're impacted by Rocky Mountain House. And so in places in the world where there's a lot of water that's being used downstream, where there's more water reuse, the problems of cleaning become a much bigger issue. And so that can, you know, be the case in a place like India, where there's a really high population and a lot of people sharing similar rivers. And I hope that reducing prices of some of these filtration technologies can help with that.
Thank you. We have a question from Elena. For any of the panelists again, what is the role of human behavior in your problem? And what would you like people to do to make your problem easier?
I could probably touch on that question. So of course, human behavior has led to the increase and the overall worsening, say, of climate change. So this climate change trend that we can see we can see climate change trends in our data. And of course, it would be maybe easier if the trend wasn't so inconsistent, or if it was easier to, if we could remove it. But yeah, so that's pretty much maybe just like a reduction in overall pollutants that result in atmospheric oscillation differences. So yeah, that's probably it for me.
Anyone else want to jump on that question?
Yeah, maybe I could also add something like regarding like the demands. Like there's a lot that actually people could do. Like first of all, the thing is like as a rule of thumb, for every like let's say every unit of power that the consumers save at the like consumer side, there's like 3 times more saving at the power plants due to all of the losses and like low efficiencies and other stuff. So everything that you do has a like triple impact eventually. And also there's a lot of like, depending on the like provinces and like countries, there's a lot of incentives for installing these rooftop power, solar power PV panels and like buying like electric vehicles. So there's a lot that people could do. Like, I don't know, like if you don't need a big truck, why not consider buying a like electric vehicle, right? With all of the incentives that is being given to people.
One, like a major impact on the water supply, of course, is that any waste that we produce ends up needing to be treated and going into the water supply. Like anything that ends up in the toilet is going to have to be cleaned. And that includes things like pharmaceuticals, which often, like you can find ibuprofen in the incoming water supply because it gets dumped and doesn't get filtered. Or even cocaine residuals show up in the water supply because it's hard to filter that kind of thing out. So in general, what we put into the waste system has a major impact on what we then end up having to clean on the other side.
Great, thank you for everyone taking a shot at that one. So we have no other questions in the chat. I have one again. In terms of whether or not AI and the use of AI is sustainable, what are some potential environmental drawbacks that you guys have come across or maybe read about, and how can these be addressed or minimized?
I know in reinforcement learning research, the amount of compute power that is used is massive. Like people will run on a computer that uses maybe 10 or 20 times as much power as the average person's laptop. And the experiment will run across dozens or hundreds of these computers. And you have researchers, like research groups all over the place doing many experiments like this all the time. So the power budget for AI research is actually quite high. And I hope that like the long-term gains from that are worthwhile, but there are ways that in the field we can be a little more aware of the impact of our own research and being a little more considerate of those environmental impacts.
Awesome. So I have a few more questions that I've thought of. Would you guys say that artificial intelligence is being used more so for climate mitigation than it is for climate adaptation?
Could you clarify what you mean by climate mitigation?
Yeah, so mitigation would more so be with preventing, so reducing the sources or enhancing the sinks of greenhouse gases, and adaptation, of course, would be how we are coping with climate impacts on the ground and reducing our exposure, things like that.
I think for my project specifically, since I'm forecasting fire weather indices to help fire management agencies better fight wildfires, it's more fire or climate adaptation.
For sure. And what were you going to say, James?
Yeah, I think there are probably projects hitting both of those categories because I mean, AI is more of a tool to be used to solve these problems than like the solution itself. And so I think as people find ways, like the problems and the ideas of solutions they have for these things, then often AI is a tool in both of those categories, like coming up with like a better way to provide an early warning system, or like the kind of forecasting for fires that are coming up, or trying to reduce the energy usage of a water treatment plant over time. Like it's going to hit both categories.
Yeah, for sure. We have a question in the chat here from Natalie. How can the water technology mentioned manage some of the present issues faced in the First Nations communities? And has this technology been tested in these communities?
So some of the issues in those communities are ones that can't be solved by an AI approach. Like in some communities, the issue is that their pipes are bad, and the pipes are actually introducing like lead or whatever problematic substances that you shouldn't drink. And so that can only be solved by ripping up the infrastructure. But in other cases, like when it's a cost issue, it can be helpful to use approaches like these that decrease the cost. And potentially, if we get to a point where an AI system is trustworthy, where you know that it's not going to make bad decisions, then that's a system that can be put in a more automated fashion. So if you've got a remote community where the challenge is getting someone qualified enough to manage and oversee a plant, then allowing an AI that can be there for moment-to-moment control with humans supervising from a distance can make it a little more possible to deploy to those First Nations communities or to other places in the world where it's difficult to get clean water.
Very insightful answer. Thank you. I don't see any other questions in the chat. I have one for Moosa. Oh my gosh, very sassy puppy. Sorry. So for Moosa, what if we don't have enough energy storage to completely alleviate the overvoltage problem?
Yeah, in that case, like we can like train our agents to do their best effort. Means that, let's say we have like overvoltage in the network, so the agents will try to charge the batteries at the maximum rate so that they can bring the voltage level down as much as possible. If that's not enough, we need to have some sort of coordination between these agents and other tools that we have in the network. So the easiest one would be to maybe reactive power compensation, or to cut down the power, because these agents are like these agents and energy storages and PV panels are all at the same location. So they can like easily communicate to each other. And if the agents cannot just solve the problems for, let's say, a few time steps, they can send a signal to the like PV panel and say that, okay, I need your help. Now PV panel can reduce the power, or it can like absorb some reactive power to help in like alleviating the voltage problem.
Awesome, thank you. Just a quick question that I have. I'm just wondering, in the literature that you have read and some of the reading that you've done, are there any countries or regions in the world that we can look to that are really utilizing artificial intelligence in terms of maybe adaptation, or some of the projects that you guys are working on, for instance?
Here, I mean, I don't know a lot from the literature. I know that our province has been investing specifically in using AI for environmental concerns. They have a water treatment focus in one area, but beyond the local scene, I'm not really sure.
Kind of a open-ended question there.
I actually recently read an article that was published, but a lot of AI for fire weather forecasting is done in India, and they're actually studying a lot of the effects that fire weather has had on Australia because of the Indian Ocean dipole and its oscillations down there. So yeah, there's definitely research happening from India focusing on Australia wildfires.
Oh, wow. That's interesting.
Yeah.
Got a comment here from Shovit. Can microplastic related pollutants be screened out and shown AI focused water treatment?
I don't know the answer to that. It would depend on, like, in the type of treatment that I'm using, which is ultrafiltration. It would depend on the size of the plastic and if it's already filtered out by that kind of filter. Otherwise, you'd need to move to a smaller scale type of technology where you could still see potentially some benefits from an AI optimizing the process, but then it's more about moving to a fundamentally different water treatment technology rather than about whether the AI can do it.
Good question. I don't see any other comments or questions. We are nearing 3:50. I think I'm going to pass it over to Eleni for some closing remarks. Thank you again to our panelists and all of the very insightful and engaging questions that we had.
Thank you, Nicole, and thank you to all our panelists. That was very interesting. I knew about some of your work, but I certainly learned a lot. I'll take a couple of minutes to try to summarize what I heard from you, trying to sort of bring the level of abstraction a little bit higher. We saw two interesting control problems. So managing energy in order to minimize the use of non-renewable resources and take advantage of renewable resources requires us to make very precise decisions about whether to store energy in a battery, which battery to use at which time in order to minimize the transfer of power from the location where it is stored to the location where it's consumed, and basically planning the locations of batteries and managing battery life. All of these decisions are highly technical and we require data and extensive search algorithms to figure out what is the optimal decision. So reinforcement learning is one of the technologies that AI at the U of A is famous for. And we saw another application in the water treatment plan where James's team's objective is to minimize the use of chemicals, to optimize the life of filters, to optimize the quality of the water. All of these decisions are probably not possible through human experimentation because we don't have enough precise measurements in our capacity, basically to run all these experiments that the algorithms are running in order to figure out what is the best decision. Humans would need way much more time. So we see our ability to control highly technical, highly complex infrastructure increase with AI algorithms like reinforcement learning. And then in Jessica's problem, we see our ability to better predict phenomena based on a variety of data. And if we know when fires will happen, then we can tailor our resource usage to fight them better with positive results about air quality and longer surviving forests, which are essential for basically a sustainable world. So there's a lot of work to do in order to better understand how things work in our environment, the natural and the built environment. There are many opportunities to optimize our resources and consume less and improve our life and comfort. And we saw 3 examples today, and I'm eager to listen to the next version of your presentation for all of you 3 researchers in our team. So I'll wrap with a couple sentences on AI for society. It is a new signature area. You know, it always takes some time to figure out how to share a screen, and I think I'm sharing appropriately. It would be very embarrassing if a professor of computer science was not able to share a screen in Zoom, but it has happened before. Of course, I forgot to introduce myself. So I'm Eleni Stroulia. I'm a professor in computer science, and I am the director of the AI for Society signature area. Dr. Geoffrey Rockwell, a professor in philosophy and digital humanities, is the associate director. And together we are working to coordinate the research activities of a big group of researchers, all of whom are interested in using AI, improving AI methods, and understanding the implications of AI to our society. I share with you here the screen of our initiatives in our website, aiforsociety.ca. And our key initiatives are collaboratories, which are interdisciplinary teams that are conceiving solutions to grand challenges type of problems. We're interested in working with teams who want to develop new academic programs in order to improve our society's capacity for the new skills that are required for all disciplines, as we saw, water treatment, firefighting, energy management, grid management. All of these can use and benefit from AI, and to the extent that we can inform our new generation of professionals with the skills that they will need to contribute in all their disciplines. That is one of our objectives. We are working on establishing partnerships with industry and not-for-profits and government organizations in order to be able to have more engaged research and more real-world impact. And we're supporting smaller projects that are sort of seeding ideas in different areas. So if you want to learn more, please register to receive our newsletter. Or if you want to be a member, whether you are a researcher or a student, please send an email to ai4s@ualberta.ca, and we'll be happy to connect you with our community and try to support you in whatever initiatives you're looking to undertake. Thank you so much to the Sustainability Council for including us in this year's event. Thank you, Nicole, for moderating, and I'm looking forward to the other panels and events this week.